Okay, so I want to show a little demonstration for the course of a notebook that I've finally, after years and years, polished up. This is actually one of the first pieces of Python code I wrote a long time ago. And so what this is trying to illustrate a numerically calculated example of the thing we were talking about today in class, the thermomechanical noise spectrum of a harmonic oscillator. So the way it works, basically I'm going to sort of simulate this. The way I do this is I create, like we talk about in class, a random Gaussian normally distributed force noise. And then I can actually calculate what the position of the particle will be as a function of time by Fourier transforming that, multiplying it by the harmonic oscillator transfer function, and then inverse Fourier transforming that. There's a couple of caveats on how many points you need. The upshot is you need a lot of points. So some of this code runs a bit slow, 50 million data points. And the other slightly tricky thing was trying to convert the amplitude I need to put into the normal distribution to get the right temperature. Actually, of course, we know from class what this power spectral density amplitude should be for a given temperature. That's what we derived. But of course, so what I need to know is there's going to be some scaling factor when I convert this thing into that thing, and I reverse engineered that is apparently 0.04, which I didn't include here. Okay, anyways, it doesn't matter. We can work it out with the temperature later. I'll probably fix this. Okay, so basically we create this random force, we Fourier transform it, we apply a harmonic oscillator response function to it, and then we inverse transform it. And then what we can do is we can get a plot that shows us what the position is of this thing as a function of time. To warn you, the Buca is a great tool which has this cool interactive plotting, but when it has a lot of points, it gets really slow. So you cannot put 50 million points into Buca. So I've limited this to 100,000 points, and then it's still a little slow. But what's kind of cool is that, so you can see here, this is what it looks like. The position is, for whatever temperature this is now, is about 100 picometers. And it kind of, the amplitude of this, it all looks like it's just fluctuating. The amplitude sort of fluctuates up and down in time. But if I really zoom in and zoom in and zoom in, I can actually see that what I'm really seeing is coherent oscillations. They're actually sort of sinusoidal-like oscillations. And in the position of this oscillator when I kick it with a random force. And the reason for that is that this is actually just another plot showing that zoom in case you don't click yourself. The reason why that is, well, the reason why that is basically because there's a high quality factor oscillator. So if I kick it once, it will take loads of oscillations. In fact, if the Q is 1,000, but 1,000 oscillations for that the amplitude to decay. So so that's why so you can kind of think of this thing as being kicked up and down all the time by this fluctuating force, and then that sort of results in all these transients that overlap with each other, interfere with each other, and give us this oscillating noise. So you can see that even more clearly if you go here. So here I have lost the reset button because I've made my window too narrow. But I have got two plots. This up here is a zoom of the very first time steps of the position of the oscillator in undergoing this as a function of time. And then down here is the force. This is actually what we started with. And so the force is super spiky. Of course, it's actually, it's random, so it's stochastic. It's actually just completely random every single point. Because the oscillator only responds slowly, that's sort of smoothed out with these extra oscillations. And what's kind of funny is that you can see places where there's more spikes in the force, but you don't see that back super clearly in the position. And that's because it takes a long time for the spikes from this force spike to the oscillations from this force spike to decay. So it's kind of like you're initiating thousands and thousands of oscillations, millions of oscillations, transients, which are then all slowly decaying and interfering with each other. That's sort of how you go from the spikiness to the sort of slow wobbling. Good. So we can also calculate the power spectral density. A nice way to do that in Python is to use the SciPy library, which includes this function Welch. You might say, why don't you just take the Fourier transform yourself and multiply it by the, square it? That gets you the power spectrum at least. I always have annoyances because I was annoyed because I was never quite get the scaling right. There's going to be some scaling of this with the sampling frequency or something, and basically SciPy Welch does that scaling for you correctly. You just give it the sampling frequency and the scaling. But also, as we discussed in class, the numerical Fourier transform of a random trace does not really give you the power spectral density. You also have to average that over a large number of sample traces. We did that in the example notebook by slicing the long time trace up and then Fourier transforming each of those and then averaging them together. That's actually also what Welch does. So this is a special technique developed by some guy Welch to do exactly that. And so there's this parameter n per segment. If you set this to the total length of the of the thing you're Fourier transforming, then there's no averaging. But if you, in this example, I'll set it to 1,000, and that means I have 1,000. I've basically sort of like I've averaged 1,000 points together. And this is what the power spectrum now looks like. It's small enough that I can plot it in Buka without crashing, which means I can fiddle around with it and slide it around and do whatever I want. And in particular, I can zoom in. I can take a look. You can see here there's a response function. It does what we think it should. I've used a full harmonic oscillator response, not just a Lorentzian approximation. So this goes to some finite value here. It peaks and goes down. And if I zoom in, I can see what this guy looks like. And that's also what we expect. It should follow the response function with some noise. And so then finally, actually, if we go all the way back up here, you can see that the amplitude, I mean, in these plots, you can see super clearly that the amplitude is fluctuating its function of time. But actually also, because these kicks are happening at random times, the phase should sort of fluctuate in time. That's not so easy to see. It's very hard for me to see where the phase starts to fluctuate in this plot. Actually, that's one use of the thing that we talked about. Other thing we talked about today was quadratures. I have some code here to calculate the quadrature representation of so this is a quadrature of a reference signal at 50 hertz. And basically what that says is I can calculate I and Q. This is sort of the cosine and the sine component of the signal that's oscillating at 50 hertz of the random signal. And of course, because it's random in amplitude and time and phase in time, then the I and Q will not be constant, but they'll kind of drift around a bit. And I can also calculate the amplitude by taking the sum of the square root of the sum of the squares. So I did that. You can see the code, how you do this. It's quite fun. But this is what you get out. So what you see, this plots both the position, the amplitude, and the two quadratures. The amplitude follows what you expect. It follows the sort of envelope of the oscillations. And actually the two quadratures, now you can see that they're sort of slowly varying a bit like the amplitude in time. And it's actually those are that's sort of the angle of the oscillation in the plane. So if I is 0, it's like I is 1, and or if Q is 0, it's like a cosine oscillation, and if I is 0, it's like a sine oscillation. And you can see it sort of go, and if they're both not 0, then somewhere in between, that's a phase in between them. And you can see that then these quadratures also shift around. That means the phase is slowly drifting. And You can zoom in a little bit more. If you really zoom in really far, you can then start to see this is now the amplitude on top, and you can see it tracking the amplitude of the oscillations. And now, if you've got a really good eye, you might be able to see, I can see from the quadratures that here I'm going to start to see a phase shift. In fact, at this point, at this point here, actually, right there, there's a purely cosine oscillation. Whereas over here, it's a purely sine oscillation. Yeah, and that I can see directly from the quadratures, and it's not so easy to see from the eye if you look at just the axis function of t. Okay, that was a little bit of an expose of this cool notebook. I will deploy it to VOCRAM so you guys can also, at least what I think is a cool notebook. I will deploy this to VOCRAM so that you guys can also play around with this. And in the meantime, I might try to fix that correction of the scaling factor. All right, see you.